Okay, so let's get started. We're going to talk about linear dielectrics. Just to start off with, the first assumption you generally make just about anything is that it is linear. Almost all interesting science today is nonlinear. There's just tons of studies that are looking at the nonlinear properties of materials, for example. Let's look at the polarization versus the E field. Now we know that we put the unpolarized material into an E field and it becomes polarized. The external electric field will create alignments of dipoles in the dielectric material. The details of the resulting P are complex, and the relation between P and E is often expressed as a materials property, and these involve empirical constants. Such a relation is called a constitutive relation. This equation here, which has a linear term in E and a second order term in E, represents a useful constitutive description. Because of the nature of materials, it is sometimes necessary to use a second order and third order tensor in order for this to work. Remember that if you have a repeated index, you sum over that index. How does this work? If you take a look at the linear term, the reason we have this is because there are certain materials where you apply a field in a given direction and the polarization is mixed. It has perhaps a component in that direction, but it also may have a component in a different direction. And so that's why this is here. The same goes for the higher order term where you have a nonlinear behavior, so it's E squared, and you have basically J and K dependence, and so you're summing over both of those constants. Complicated materials sometimes have to require this. If you look at the materials that we're going to be discussing in this course, we can ignore this term, and we can make this a simple constant times a value of the field, a vector value, which is related to P. So it's important to realize that the chi's are useful, measurable constants, and they're associated with a particular dielectric and describes the behavior of polarization in an applied E field. I just want to give you an example which you're probably more familiar with, and that's Ohm's law. There is no law of science or physics that gives you this. This is an empirical equation. It turns out that you can derive this kind of behavior if you get down into the nitty-gritty of the way electrons move through a material. Basically, you have measured variables depending upon a constant, which is also a measurable constant, but it is material dependent. And another thing is that R depends on the dimensions of the resistor, in other words, the length and cross-sectional area. A more general quantity is the material's resistivity, which we call ρ. This does not depend on geometry. Remember that R can be related to the resistivity by multiplying by the length and dividing by the area of the resistor. Okay, well, as you know, the resistivity for metals is very, very small. The ρ for insulators is huge, but not infinite. You can put very high voltages across insulators and measure the current through those insulators. In some instances, for example, for fixed voltage, the resistivity is not a constant, but depends on the current I. Well, let's go back to linear dielectrics and what we mean. In materials that polarization is proportional to the electric field, in other words, they are linear, and in the same direction, we have this relationship here, that the polarization is directly proportional to the applied E field, and then it has this combination of constants. We're familiar with epsilon zero, the permittivity of free space. We were introducing a new quantity, which is called the electric susceptibility. Now there's a caveat in this equation, and that this field here is what we call the total electric field, and it's due to both free charge and polarization. And sometimes we describe it as the sum of the external field and the internal sources creating this combination of field. This complicates things, but we'll try to get a handle on that. One more time, the constant of proportionality, chi sub E, is called the electric susceptibility. Now, materials in which the induced polarization is proportional to the electric field are called linear dielectrics. Material which obeys this law here, where the polarization is proportional to E, those are linear dielectrics. So here's the equation again, and to emphasize that E is the total electric field due to free charge and polarization. So let's talk about E. When we apply a external field due to free charges, E sub free, to a linear dielectric, the above equation for P does not really allow us to calculate P. Why? Well, just a warning, we're going to go in circles, so you're going to have to hang on here. When we apply the free electric field, it polarizes the material. This polarization generates its own E field, which changes the total field inside, which changes the polarization, which changes the E total, and it just keeps going. How long do you stay in the loop? Well, until you get tired, I suppose, but we're going to try to find another way. Just to mention, in computer programming, you watch an infinite loop flying by on the monitor, say, and then you hit the panic button. We will see that D is going to save us if we can figure out how to use the free charge to get D. So let's introduce a couple other terms which are handy. LIH stands for linear, isotropic, homogeneous materials. So what we have then is P given by the linear dependence. Let's define our old friend D. This is what we defined it before, epsilon 0 E plus P. This is the true field right here, not the external field. Chi sub E is the electric susceptibility. If you look at this here, we have a way of writing D and include this term here. So here we go. P is equal to this. D is equal to this. So for P, we're going to put this into the equation. And that's what we have here. Those two terms that now have chi in the equation. Well, we can factor out E, and so we're left with this relationship here. The product of epsilon 0 times 1 plus chi sub E is equal to the total permittivity times E. One more time, E is the net E at position R inside the dielectric due to all sources, including capital P itself. And here's the definition of epsilon. It is the permittivity of the material. If you take the ratio of E to E0, this gives you the relative permittivity, and that's also equal in magnitude to what we call kappa. Kappa is the dielectric constant. Epsilon R is the relative permittivity. So one more time, the ratio of this is equal to this. They're equal in magnitude, epsilon R and K. And remember from what we have up there, this is equal to 1 plus chi sub E, because this is epsilon, here's epsilon 0, and here's 1 plus chi sub E. So if you look at this, you take the ratio of this entire thing divided by epsilon 0, this is what's left. But that's also equal to epsilon sub R. It's often easier to work with a capital D, which satisfies Poisson's equation in the following form. The divergence of D is equal to rho sub F, where this is the bulk free charge density. Realize that if we have surface charge, we can write it in terms of a bulk charge using something like a delta function. These relationships, although they're fairly simple, you've really got to look at them, you've got to play with them, you've got to write them down and memorize the basic relationships that are on this page. And just to motivate you, if you understand what we're doing here, and for the next 1 or 2 sections, you're going to be able to get a job. So let's re-examine the shielding effect due to a dielectric, and we'll do this in terms of some of the relations we've developed. So what we're going to do is consider a volume V entirely filled with linear dielectric with a dielectric constant, that should be a kappa. The polarization P of this material is equal to the linear relation that we gave before. It's proportional to E everywhere. Take the curl of P. That's equal to this constant times the curl of E. But we know that that is equal to 0. If If that's the case, then if we start with D and take the curl of D, let's see what happens. We have the curl of D equaling this quantity here, and we can factor out epsilon 0 and take the two terms, curl of E plus the curl of P. We've already shown that this is 0, so the curl of D is equal to 0. For linear dielectrics, we actually get a curl of D equaling 0. That's generally not true. So for a linear dielectric then, we have this, and we've already said that this obeys Poisson's equation in this form. If you go back to the electric field that's generated by free charges, we showed that the curl of E free is 0, and the divergence of E free is equal to this quantity here. By the way, this happens to be the first Maxwell's equation. And so we said that if we know both of these, then we have a unique solution for the E field. So if we look at D then, if we have rho free equaling this in terms of E, that being equal to this quantity here, we see that this is indeed equal to the divergence. So that's consistent with D equaling epsilon 0 E free. Both sides are consistent with the 0 value for the curl of D and the curl of E free. So the displacement D can also be expressed in terms of the total field inside the dielectric, what we call E total. So remember what this is. This is the field inside the dielectric that is due to the polarization of the dielectric plus the external field, the E free. So let's first get that relationship. So we go down to the D definition where it has a term which is E0 times E total, the field inside the dielectric, plus the polarization. Now we've already said that the polarization is going to be defined in terms of this set of constants times E total. Well, we factor out epsilon 0 and we factor out E total, and we're left with, of course, this expression here. And if we remember, this is epsilon r or kappa. They're equivalent. So epsilon 0 times epsilon r gives us the total permittivity times E total. Okay, now if we couple this with D in terms of the free field, which was given here, we can see that if we set these equal, so D equals this, D equals this, then we can write epsilon 0 E free is equal to epsilon E total. If we now solve for E total, we get this expression here, and we recognize this ratio as 1 over epsilon r, the relative epsilon, and that's equal to 1 over k. Remember, these two are equal. We got this whole thing by using D, and that's what I meant by sometimes D is easier to use than other approaches. The other thing, of course, was that we had linearity, and that's really where D is most useful. So the presence of the dielectric material reduces the electric field. This is the shielding that we mentioned in this panel here. E free is what E would be simply due to the surrounding electrodes. This is the free charge. With the dielectric present, the space inside the dielectric has an E total that is reduced from E free by the factor of 1 over kappa. Just to go through this Li nomenclature, this is a subclass of dielectrics. It has the following properties. It is linear, so this is just like what we said before. It's linear in the fact that the polarization and the E field are proportional. What that implies, these constants are independent of the applied E field. Is goes with one of them, R goes with both. Isotropy has to do with the fact that these do not depend on the orientation of the material. It is independent of the direction of the E field. So that means the polarization always goes in the direction of the E field. Homogeneity just means that these constants have the same value at all points in the dielectric. For the majority of dielectrics, E sub r, epsilon sub r, is found to vary with temperature and the frequency when the applied E field is oscillatory. This is very important at high frequencies. The value of epsilon r in a steady E field is known as the static relative permittivity. Likewise, kappa in a steady E field is the static dielectric constant. And don't forget that in magnitude those two are equal, and they're unitless. You can find a table of dielectric constants, and clearly you'll see that they're material dependent. There's a long list of these at this website. If you scroll down on this web page to dielectric constant for selected materials, you'll see this table. What I'd like you to look at is that the range of kappa is very large. Big values of kappa show up for very special inorganic crystals that have unique non-cubic unit cells. I'd also like you to look at water. It has a medium kappa. And I just point out that your body parts are made up of water and are close but usually smaller than the kappa for water. And the decrease comes about because of all the gushy things that are in your body.